that. All right. What are we looking at?
Hurricanes?
Hurricanes. Correct. What is different about them?
Different hemispheres?
What's that?
They're different hemispheres.
Different hemispheres. How do you know that?
One's spinning the other way than the other.
One spinning the other way than the other.
So one's counterclockwise and one's clockwise.
Right. Which one's which? Not which one's clockwise and which one's counterclockwise. Which one is which?
Oh,
Which one is in which hemisphere?
Okay. The right one's the north.
You think this one's north?
Yeah.
Raise your hands for this one's north.
Oh,
Okay. Raise your hand for this one's north. Raise your hands for no. I'm not gonna raise my hands. Good. At least you're honest. Okay. So we're gonna talk about basically the places that I want to go with this is we did gravity waves a little bit, and we'll finish up that discussion. But if you saw in the content schedule, I put in the exact chapters we're going to be looking at. So we're going to jump around a little bit today. We're going to go into some discussion of the Coriolis force, and you'll be really upset to learn that means there's more terms in the Navier-Stokes equation. Oh, fuck. But then we'll talk about what are called geophysical flows, and we'll describe how this could even happen at all, right? And then you'll be like, wow, I understand hurricanes. And you'll be like, I could teach someone at the beach about a hurricane. Right?
so geophysical flows, that's just like how the earth is facing the same flows as like a full world fluid motion.
And as I mentioned to the folks who were here on time, is this book, when you see this book, you know that Mateo's having a bad day too, because he forgot his actual book. So I had to go and I have to read this one, which is a piece of crap, essentially. It's floppy and doesn't have my notes in it. So if the class sucks, just remember to put that in your FCQ. Constantly made fun of us for not arriving on time and also didn't even bring his own book, right? Just write that whole line. Okay. Questions before we get started? Have folks looked at the homework already?
Yeah.
Okay, what do you think about the first one? You didn't look at the first one, did you?
Yeah, it was basically, I know I looked at it. Swear to God.
This one's so easy, folks. You just open the book, you read it, you do it. The second one, not so easy, but you got to do the first one. Okay.
Wait, so okay, with you said it was going through these two or like
No, it was do the top one. Everyone does the top one, which is why I expected you to have done the top one already. And then the second one is a choice between doing the mathematics of the second one or coding up the example that we saw in lecture.
Okay.
Okay. Questions, comments, concerns? Okay, ready? You're gonna do another homework. Never stops. Let's remember a couple things. The check-ins were really good last week. If you haven't done a check-in, please make sure that we find the time to do that. I got consistent feedback that folks have definitely fell out of favor of the progress reports. That's a tool. That's a way for you to directly communicate to me. It's not a requirement. The requirements are understanding the material and learning. Okay, if you feel like it's extra work that doesn't help you learn, fine, don't do it. I don't give a shit. Right? What I don't want to see is I don't want to see people just putting off the homework in lieu of other classes. So the end is 9, week 12.
Yeah.
That means I could throw a rock and I could hit the end of the semester. So don't think about it too hard.
That's good.
So that means that we need to finish these homeworks sooner rather than later.
Yes.
Because otherwise you will have all of the homework to do at the end of the semester.
Not
And we know how that goes.
Not
Well, zeros. Okay. Any questions? What's that?
Alex last semester told us that he did homework for like 56 hours.
Yeah.
That's
right. He didn't sleep.
Right? Yeah, he was like 50 something.
Yeah, that's really good for your mental health.
Yeah.
And you definitely helps you in the next semester when you need to use that material. I'm sure he didn't regret that at all. Okay. What's this? John.
Yes, that is the continuity equation mass.
Good.
And we have diffusion on the left and advection on the right side of the operation. And the zero means that we don't have any sinks or sources.
Good. 98% correct. Was the one mistake? Okay, read what was the mistake you made?
There are no sources of things.
No, that's what he said.
Yeah, yeah.
Oh, sorry, I understand.
Eduardo, what did he say wrong? I didn't hear anything wrong.
He said that the first term was the diffusion.
Ooh, oops.
Just kidding.
And what is it instead?
The steady or unsteady.
Steady or unsteady, that's right. That's right.
Okay, yeah.
Well, I do then.
Okay, let's go.
That one is the change in pressure intensity.
What's the whole thing called?
Oh, the Navier Stokes.
Navier-Stokes equation, and this is
The change in pressure, the change in intensity.
pressure.
Um.
Also starts with a P, but that's
Yeah.
linear dynamics. We're not doing linear dynamics.
A leg kick?
Momentum. He is momentum.
Oh, yeah.
Oh,
Yeah.
wait, were you like confused about? Oh,
Yeah, I was confused about.
Oh,
Okay,
Yeah, it's not
keep
confused
going.
about-
And then it's with, pressure gradients, the body force and diagonal and off diagonal.
Good.
Which is compression and rotation, right?
Anything he's missing? Okay, Kobe, you ready?
Oh.
Go for it.
So that's the caloric equation.
Uh-huh.
And it's the conservation of energy.
Uh-huh.
And then the low E is the internal energy, the other one's the kinetic energy,
Mm-hmm.
then we have the outside body forces.
Mhm. Sure, keep going.
EDB, it's like how we change the box the first, yeah, that one.
Okay.
That's how box changes. The next one is, I think it's like this motion.
Okay.
And then leave the next one's like pressure on one side is like on the other side, so it's like pushing a box.
Okay.
I don't know the difference between the two T's. I know one's like heating it up almost, and the last thing's heat flow.
What do you get wrong? Yeah. Yeah, so he's a little ambiguous here, right? So because he didn't want to commit to either one of these, and the hand motions were kind of hand motioning, right? This one here was PDV, that was right. This is pushing the book, because this is the push of the book, to push the book, right? So this one is not to push the book, the push is outside. This is PDV, and this is the push, okay? We're gonna remember that now. This piece and this piece, he didn't want to commit to. That's totally okay, but he did do this here, and that's right. But also if you do this, right, this is how you get away with just making whatever hand motion you want. So this one is this, and this one is this. Yeah. So remember, you're not spending enough time in the pool. Okay, we got to go to the pool with the friends and you splash them in the face. Drag the water with your hand, right? Question?
Is it okay to say that that's the viscous work and that's the diffusive work? Or
Yeah,
not?
yeah, absolutely. So in fact, when you think about it, in terms of energy, right? So this would be the work that goes from the kinetic energy into the internal energy. Whereas this is usually the work either done by an outside force from that parcel in changing the parcel itself. Who means? All right, who's ready for the last one? Reed, you ready?
Yeah,
What is it?
that's how it works.
Okay.
And the first part is advection, the second part is.
Of what? Of vorticity. Does everyone agree with that or not? What do you miss? right? No caveats, any, you can always use this, it's always applicable. What's that? Vorticity is always correct? No, why is it not always correct? No, because I can generate vorticity. Does this have to do with viscosity? Right, so these pieces here disappear and they're not present here. But you do need it, right? Well, if the fluid's at rest, you can still generate vorticity. Right? Remember, this is using streamline and vorticity line formalisms. Is this applicable at a boundary? Not always. Okay. So we have to think about scalings in order to make these correct. There are some actual rules that you can read in the textbook, a list of conditions that are necessary in order for this to be accurate. And this is what we call an approximation. Okay, this is also an approximation, specifically these terms here, right? Because the relationship between those terms defines whether we're talking about a Newtonian fluid or non-Newtonian fluid, right? The relationship here. Okay. And since you're all really prepared, and you certainly were updating the content schedule at every moment last night, and so once I updated the content schedule, you went and you did the reading ahead of time, right?
Yeah.
So what's this one?
Oh.
Oh no, Mateo! Started to like you. Aha! It does look very much like the momentum equation. Good. What's different about the momentum equation here? That's right. Since you spoke, now you're in trouble. You can do all that.
Oh,
I think there's like, is that a second derivative?
Here or where?
On the top? I don't know, it's like little primes, or is it?
Oh, the little primes.
Those from a different.
Yeah, that's weird, right? Different
Frame?
frame. Correct. So there's a different frame, and in fact, you can see it here. This is the O1, 2, 3 frame. Okay, that's our first hint.
I think the omega symbols are those streamlines?
Yeah, it's really annoying. I got omega up here. Got omega here.
I thought those were the streamlines. For path lines.
These ones here? No. We're gonna use a different terminology for that.
Yeah.
Those would be your size and your phi's and your size. Our omegas here are usually, the capital omega is only gonna mean rotation of the system. So in fact, we'll be talking about today, non-inertial reference frames. And just like we've done before, I have here, this is the same term, right? Gradient of the pressure, but in the rotating frame or in the moving frame. Here I have PG, that's going to be up here. You have these fun new terms that we're going to add. Aren't they cute?
Right.
We're going to say no. And then you have this one that we're just going to add onto here. We're going to pretend like that doesn't exist. Okay. Everyone excited? Okay. So let's start by talking about, we're going to take a step back. Okay. We're going to remember what we did on Wednesday, as though the classes are connected and the material builds on one another. Okay. So let's think first about, we were talking about waves, right? And we had this idea of an interface wave, which was a wave that forms due to surface tension between, say, a liquid and maybe a gaseous fluid, right? There's a nice little example in here to get to waves at a density interface, where they talk about, well, what happens if you have, say, two types of, let's say, water, one that's more salty on top of the other ones, like this. So here you have salt water on the top or bottom?
Bottom.
On bottom.
Is denser.
Right, denser. Okay. Now, I didn't say anything about temperature, so we can flip this around. but we assumed that they were the same temperature. Okay, if this one was actually warmer, right? So let's say the salt water was warmer, where would it be?
Still have to go
On top.
Okay.
What's more important, temperature or salinity? Temperature or salinity? How much salt? Say salt, raise your hands for salt if we're more important. Not for drinking. For how dense it is. Okay, you're all wrong. Temperature is the most important thing that we need to talk about. Salinity makes a very small fraction of the total density. It is quite important, okay? But usually when we think about gradients, say in the ocean, we'll talk about geostrophic flows a little bit later. When you think about the composition of the ocean, it's mostly dominated by the temperature. And in some small cases, salinity becomes important. Okay. Okay. So let's say we take a medium here. And again, we're going to use the same rules we had before, some small perturbation. Okay. And you have a fluid on the bottom and you have a fluid on the top. Okay. So one thing that you want to see here is that you're going to assume some solution types. Right? What was the solution type? Oh my God, look at this chart. It's so beautiful. So happy right now. Okay. Okay. All right. Solution type. I want to know psi, whatever this thing is called. I don't know. What should it look like?
the equation.
Like look at what it looks like. What's the vibe?
Like a kind of sort of wave.
Like a wave.
Yeah.
Good, right. How do I describe a wave?
Use.
Sines and cosines. We like sines and cosines. Okay. And now that we're all adults, sines and cosines are for high school. Right. What do we use instead?
Sinusoidal.
Gosh.
Sinusoidal.
Sinjin Kosh? That's getting crazy. I don't want to do that.
Sinusoidal.
No, sinusoidal is not it's a sine and cosine. It's the same.
Complex exponential.
There we go. Let's make it tricky looking, right? Okay. So we can do something like this. And the only reason I want to say this is because generally speaking, right? Generally speaking, when I talk about this, right, you have a complex exponential, and this becomes a cosine and a sine, right? Do the Euler, and then and what you can do is you can always solve the wave equation, or you can solve as a Poisson equation, you can solve what you want in terms of complex exponentials, and take the real part, and the real part will be the meaningful part. So generally, we'll say something along the lines of, seen this nomenclature before? RE, the real, as opposed to IM, imaginary. Huh? These exist, but they're fake. Okay. And the nice thing about these is then you don't have to choose a sine or a cosine. You can just have that, and the phase is going to change naturally, right? Okay. So what we can do here is we can talk about the boundary conditions, and we say on the top you have one fluid, on the bottom you have another fluid. They're not going to mix. But I do know that I have to solve the Poisson equation in both. And so you could do that if you wanted to. You have something like, you just write it good. Those are different, sorry. Okay. And then when we look at this picture here, and we think about what do these d phi dz's mean? D phi dx?
Curvature.
Right, but what were the physical interpretations? What was phi again?
Is that the stream line?
Yeah, something like the stream function, right?
Okay, stream function.
There's a relationship between the velocities and the stream function. Does anyone remember what those were?
It's like E sine dx equals E or something.
Yeah, exactly, right. So it's something like this. Right? And so let's look at this one here. We have this natural interpretation here. Okay, this thing is going up and down, say at a specific location. You would call that what? Something that was up and down. U, V, W. So that'll be our W, right? This thing going up and down, that's the definition of our W. And because one of the fluids is on top of the other fluid, okay, this fluid going up, right? This fluid going up means this fluid has to go up. Do they go at different speeds? No. Do they go in opposite speeds, opposite directions? No, they're going together. So the speeds are the same. So d eta dt is the same on both sides as the phi just at this line, right? And we can say that. A little bit trivial, but it's okay. I don't know, whatever. Sorry, just the garbage. Similarly, you can write the equations of motion. Something like that. Okay, that's at the same interval. So those are both true at the intervals. Right? Okay. And then we can just use the solution type. We know that it's going to be wavy. We understood from the interface wave that we probably have some condition on on Z. So Z is the one that goes up and down. But we won't let it get too far away. So you can do something like this. Phi 1 is just A, e to the minus Z. So before this was our like cinch and over that like Koch stuff, right? But it has the same type of functional form. Okay, in this particular circumstance, that was our cinch type variables. And then you have e to the I ax minus omega t. And that's our wave part. Wave moving left and right. The amplitude is modulated, by an exponential. And the opposite is true here for 2. So the one above, this will be B, E to the K, Z. Is that a problem? Imagine that those are your dittos right there. I just want to talk about the exponentials here. Is that a problem, KZ? It's going to make that wave blow up to infinity? No, why not? Oh, I didn't write it good here. This is z equals 0. The z is negative in this direction and positive in this direction.
Wait, repeat your
This is
question.
phi 2. Or sorry, this is row 2. Phi 2 is applicable here. This is row 1. Phi is applicable here.
Is the horizontal the?
Yes, yeah. Yeah, it's the same picture that we had on Wednesday.
So what was the question again?
So the question is this a problem? Right, so here I have a decaying exponential. I love decaying exponentials because they basically go to 0.
Mhm.
Z gets really big, amplitude gets really small. So for example, if I go really high up here, the wave amplitude is going to be small.
Okay.
Good, I want that. But if I go down, now I'm looking at that second equation. Am I worried? Why not?
Because he's negative.
It's these negative. It's built into our coordinate system, right? Right here.
Wait, so
Okay.
for B it's below Z,
Yeah, because this is a different fluid,
but for A it's just above.
right? Because this is phi 1 and this is phi 2. And these deviations, they will exist. They'll be the size of eta. But if they get very large, then everything is broken down already because this is a small wave approximation, right? Large wavelengths compared to the interface that you're talking about. Small amplitudes, right? Okay. All of that is essentially to say that you get this wonderful dispersion relation. Okay. Very straightforward. Assume those are rows. But I did this right. Okay. Okay. What does this even say? What was the dispersion relationship again?
Wasn't it omega is equal to square root of G, K, and H, and then in the parentheses it's K times capital H.
No, what did it mean? Remember, we hate letters in this class. We only like meaning. Yeah, it describes the speed of the wave in terms of Ks, wavelengths, frequencies, right? It's this fundamental relationship between the property of propagation versus the property of the wave itself, right? Because it's in a fluid medium. Sometimes waves are non-dispersive, which means what? But what does non-dispersive mean?
Different wavelengths separate from each other.
They don't separate, so they all travel at the same speed. Whereas a dispersive relationship, which we almost always have, here I have a relationship between omega and k. So this must be dispersive because it means that
Waves speed up as they go.
other way around.
Oh, they slow down as they go.
No. Think about what the important part of it is.
Oh, okay.
The important part is that the wavelengths prescribe things will have different speeds.
Mhm.
The motivating factor here is the wavelengths, not the speed itself, right?
Okay.
Does that make sense?
So we're saying that the speed is proportional to length.
Speed is proportional. Yeah, kind of. You're gonna have a modified. This is basically a modification right here. We end up calling this something like theta. It's just a ratio of these two densities. And then it's the same type of dispersion relation that you had for a normal interface wave. Now, typically, when you think about those normal interface waves, imagine air density compared to water density. Right?
Mhm.
Theta is 1, essentially. If they're exactly the same, what happens?
It's just
0. Yeah, what does that mean?
There is no interface.
There's no interface waves.
Is that?
Wait, was that true?
Yeah. Well, is that garbage? So the interesting thing is that yes,
Oh, yeah.
if you think of if you to answer your question, yes. Thinking about having two interfaces that don't mix doesn't make any sense if the densities are the same.
Oh,
The important part where we started is that the interface is different.
okay.
Sorry, my brain just absolutely shut down there. So one thing we want to think about is that internal waves, right? They will end up having a smaller frequency. Because imagine for a moment that wave or this salinity talked about, there could be a difference in salinity. Let's say it's about a 10% difference. Okay. So this one is maybe 1 and this one is 1.1. What does this end up being? In terms of bigger or smaller than 1?
Oh, that.
Smaller than 1. Okay. So what we're basically talking about here is that the internal waves, so you're looking at your ocean, okay? The ones at the top, those are the ones with the fastest speed. They're setting your limits. As you go deeper into the fluid, let's say you have stratification, your internal waves are going to have less, okay? Because they're all modified by this. Okay. Okay, so now let's talk about stably stratified fluids. Okay. Did that make sense? Because we're just going to keep doing that again. We're going to look at a different form. Okay. All right. Yeah.
Is it a good thing if it's less than?
It's not a good thing, it just is a thing,
Okay.
right? You don't have a situation normally in which row 2 is up here, bigger than row 1, right? Normally you have lighter stuff on top of heavy stuff, right? And in that circumstance, the internal waves will not propagate as well as the ones right on the surface. Okay. We're going to do one more thing here. We're going to talk about, we had these two fluids on top of each other. You said, well, what if you have this whole atmosphere stacked on top of itself? And this is a theme I want you to think about today, because we're going to get to geostrophic flows right after we get to rotation. So don't let this come in and then immediately go out. Okay, hold on to it for at least an hour. Okay. So we wanted to think about, let's say you have some flow and the scale lengths were really important. And I know I ran through this in like 10 minutes. So we're going to spend a lot longer thinking about it. But if the horizontal length scale, right, is very large compared to the vertical, you can think of each layer as acting sort of independently, very little motion in between the layers. So it's not like our boiling water in which the length scales horizontally and vertically are the same, and the mixing occurs equally in both. If you think about what we call a stably stratified atmosphere, that is to say layer after layer after layer, okay, you can have motion in each of the layers. Maybe one is going this way, the other one's going like that. No big deal, right? They don't even care about each other. And the only thing that changes as you go up, maybe is temperature. Let's use an ocean now. I know that we just talked about this in the context of water, but these are true in both circumstances. Okay. So as I go up in altitude, let's say the first 40 kilometers, we're not going to get into anything about the stratosphere because it's annoying. We're just going to let the temperature change. Temperature is going to go down as we go up. And as the temperature goes down, okay, the pressure is going down and the density is going down. Does that make sense? Yes, it does make sense. Why? Why is the density going down even though the temperature is going down?
There's less pressure.
Less pressure, right? Remember what the pressure comes from. Pressure comes from the column above you. So counterintuitively, you always think, oh, it's cold, it's going to be denser air. That's not the case in a fluid necessarily. Okay. You move up in altitude, the stuff pressing you together is less dense, there's less pressure, and so you are less dense. Okay, density decreases. So now we're talking about a stably stratified atmosphere. It's hot near the bottom, it's dense near the bottom, and it cools and becomes less dense. Does that make sense? Everyone's picture is the same picture? Okay. So we talked about this wonderful set of equations. You have something like du dt is minus 1 over rho naught dp, oh god, dx. And you can have the same one for, I guess I don't even need to write this, whatever. It's too late, I've committed. And then this one is the one I like. These rho naughts mean
Your preference density?
yes, exactly right. Exactly right. What does potential density mean? That seems fake, right? Potential density?
The density map of the one area.
We talked about this in chapter 1. I'm shocked that you don't all remember it. So instead, when we think about the layers of the atmosphere, okay, and we talked, for example, about a box of gas. So let's say this is altitude. Okay, and it's also sometimes density. Density is decreasing as you go up. So let's say this is density and it goes like that. Right? Let's say that's a curve. That's a really bad curve, but let's assume that that's a curve. And I take a parcel, okay, and I bring it up to here. Okay. We say potential density would be the density that we would expect it to have there if we moved that parcel without adding any entropy. So as long as this motion is isentropic, remember those words? Those are fun words. What does this one mean? What stays the same? What? Entropy. En. So iso, same. Entropic. Entropy. Latin. Okay. So let's go over here. We're talking here about a reference potential. This is a potential density, right? And these will be deviations from it. So for example, here, rho g with a deviation from your potential density from whatever parcel you created, right? Lose anyone? Yeah. Yeah. Okay, so my box is down here, my bag of chips, and I'm really excited to eat them on the plane. I take them on the plane, I bring them up, and the density of the air inside is now different from the density outside. The density where I brought it to is low. The density inside is high. If I did it through a non-entropic process, I would have to slowly let that air out. Right? In practice, what really happens? Your bag explodes. That's an entropic change, right? Okay, that's a non-reversible change. But I can't get the gas to go back into the bag after that. And in fact, you know, if I slowly go up and down, and the bag's already open, I don't notice that my chips in the bag suddenly are moving around because of the addition of more gas, as I just said. right? You see the difference between the isotropic and the non-isotropic paths there? Okay, so going from one place to another, you have an expectation of what the density will be. And that's your potential density. Okay, in this case, when we see, rho with a little, you'll either see it with a little dot like this, or you'll see it with a little theta. You go into chapter, I think it's like 110 or something, potential density and potential temperature. It talks about the different ways that we think about, say, adiabatic rules, how we transport gas up and down, and we think about what gas temperature and pressure they should have. Okay, you survive?
But that's still not.
Yeah, or well, rho theta is by definition the potential density. Yeah.
And what was the regular rule again?
The regular rho is the one that we're talking about for our parcel. No subscript usually means our parcel. In this particular circumstance, we're talking about a reference. Okay, but I'm adding the idea of potentials to you right now, because I think we'll have enough time to see it in about 25 minutes. Okay. Okay. Good. So that was true. We also know that this is true. Because I'm constructing the problem and I choose it to be this way. Okay. It's going to be a little unintuitive, but I'm going to talk you through it. What does that mean?
No net velocity. Only the big block of acceleration.
This is also written as
Gradient yeah. Okay.
and that's a statement of.
What's this?
Nope. It is true that there is no verticity here, but that is not what that is a statement.
Oh, okay, got it. There's no vortex.
What's that? It's not a diffusion statement. So these are spatial gradients. So let's look at them side by side. Okay. Here, the u dx is how x is changing, or how u is changing in x. This is how u is changing in y. Sorry, how v is changing in y. And this is how omega or w is changing in z. Okay. If I want to change u in x, I have to take it away from one of these. What does that sound like? Yeah. Yeah. So if I have u and it's moving this way, and I want to change it in x, so this is u in the direction of x, and I want to change it, I require it to come from the changes in y and the changes in z. Right. Change it this way, it has to change this way or this way. Okay, so now you're thinking of changing volumes. That's close, in the right area. This is talking about compressibility. Specifically here, we're talking about mass conservation. That the changes in the velocity here are coming in the direction of the motion, are coming from being taken in the other directions. This is a mass conservation statement. Does that make sense?
It's just looking at that.
Well, yeah, just the row here has been divided out. Because if it equals 0, then it doesn't matter. Does that make sense?
Yeah.
Okay. Okay, so then I did this whole song and dance. And I I said that we can do some really fun stuff here. We can assume that we have something like rho bar. Remember that? Does everyone hate this already? And that can be something like rho naught plus rho. Right? And similarly, you can do this with, that's a P, sorry. Okay. And this process was called
Linearization?
Linearization. Why? Yeah, it's a linear. It's a line. So the mean value plus a small perturbation. You can also think of this in terms, if you're thinking about classical dynamics, this is perturbation theory. Okay. Small value, or sorry, mean value plus a small change. Okay. And then I said, okay, apply this everywhere. Cancel everything out. And you end up with something that looks like this. Oh, let's do it this way. Sorry. Let's be consistent. This is what they want to use at average form if you're following on the book. Average being a bar. Okay, and so this is talking about small changes to the background density. Or sorry, small changes to the density compared to the background are just going to be equal to the flow times this weird ambiguous thermal gradient. You don't know it's thermal yet, but it will be thermal. You'll remember that if you remember your chapter 1. Okay, and then I made a statement like this. N squared exists and has a really fun name that we all like saying. What? That's not fun. Fun name. Name of someone. Or 2 people, I think. Okay. It's called the Brunt-Väisälä frequency. What? What does that mean? No, those are names. Not all names are English. Oh, does it? No, it doesn't mean anything yet. No, these are I think these are 2 people. We'll find out tomorrow. We'll find out Wednesday. I'll do my background research. But what we're looking at here is something along the lines of we know that these are some wave type equations, right? And I gave you an interpretation for what the hell was going on here. I said we're going to use n squared, and it's going to be defined by properties of the fluid. Now, G is the buoyancy, right? Associated with the buoyancy, rho naught, and then something about dPdZ. And when we think about dPdZ in a stratified fluid, remember I told you all that we were requiring the density to change as a function of altitude, probably because the temperature is changing, right? Those are the things we went into. So surprise, surprise, we got the answer that we wanted to. There's something in these equations that depends very strongly on this. Now, we don't have a physical interpretation for what n squared means yet, but let's just jump ahead really briefly and to look at how you would write the dispersion relationship. Okay, like you're welcome to go through this. You'll learn about what a horizontal Laplacian is. It's cute. It's just the gradient, but only in the horizontal. Okay, so instead, you end up with the dispersion relation that looks like this. And you say, well, what's the theta there? I can just write it like this. This will be your z. This is your xy plane. I'm not going to draw both of them. If that's okay. Okay. And then you have, let's say, lines like this. Okay, these are going to be lines of constant phase. And you might have, say, a particle moving back and forth. Maybe at an angle. And this. Okay. And this one here is going to be something that becomes k, big vector. And so that properly. That's supposed to be right angle. Let's assume that I did that right. Oh, Mateo, that's not very helpful. I don't get it. Who feels that way? Good, good. Okay. So let's think about what I'm writing. There's some particle in the fluid. Okay. It's making small perturbations. We know that because it's a wave equation. We already said there were going to be small perturbations. Okay. And what we were looking at here is we were trying to write a dispersion relationship, which describes how the waves themselves are propagating. So to understand what the hell theta is right there, and maybe even what that large K could possibly mean, let's think about the limits here. So what does omega equal n mean? So this is, n is a frequency. I told you it's the Brunt-Väisälä frequency. Let's imagine that cosine theta equals 1. When does that happen?
K on the x-axis.
When K is on the x-axis, good. Okay, so K is oriented to the x-axis and theta is equal to 0. Good. And so the particle is only doing what? Up and down. Okay, there's some perturbation up and down. And so this here, n, would mean what in that circumstance? Yeah, so how much is oscillating up and down, right? We thought about it in the context of this omega t over here. Is the frequency of the wave in the first place. And now I'm describing the frequency of the wave. Okay? But that frequency of the wave depends on the internal parameters of the fluid itself. So depending on where I'm looking in the atmosphere, what the specific local density is, and what the temperature gradient will be, temperature, pressure gradient, I'm going to say those things interchangeably because I can't help myself, okay? The properties of the fluids can only support the largest frequency being n. Is that a dispersive relationship? No, why not? Nothing to do with the wavelength. Doesn't care about the type of waves. These are non-dispersive waves in a stably stratified medium. And the highest frequency you can have is set fundamentally by the fluid itself. Okay, well, let's think about some other angles. What happens when theta is pi over 2 or 90, I should say, sorry.
Oh, then it's horizontal, oscillating, it's oscillating horizontally.
What does that mean? Waves moving back and forth like this, right? Just what happens over here if the theta is pi over 2? How do I interpret omega then? Cosine of pi over 2 is 0. So omega is 0. Is that meaningful?
Yes.
Why is that meaningful?
Then that means there's no oscillation. At that point, is that just like a still fluid or something?
Yeah, that's the question. Is it a still fluid?
Is it because omega?
So this is W, right?
Oh,
Even though it's very poorly drawn. That's
it.
omega. This is W.
Yeah.
W is the vertical propagation, and this is the dispersion relation in the types of waves that we can support. The reason I'm showing you this here because it becomes a property of the fluid, and I'm demonstrating the dispersion relationship. You're welcome to work through the linearization yourself, and you see how it pops out. But I think in order to interpret what we're actually seeing here, what type of waves can exist in a fluid, we have to think about the dispersion relationship as a whole, right? So we understood that when the perturbations are only up and down, you get the Brunt-Väisälä frequency. But in fact, perturbations can be in any direction, right? So K, not surprisingly, is the direction, that big K, is the direction of all your propagating waves. Let's say you have some amount of waves going this way, and some going this way, and going this way, And this way. And the total sum is like that. Okay. Right. You can break that down into expression. Okay, in the direction of z. Okay, in the direction of x. I would do the propagation in each one because the waves don't interact.
Where are the diagonal lines again?
Those ones there? That's the path of the particle that I cared about.
No, I mean the CT lines.
Yes, yeah. So see that little particle that I made? Those are lines of constant phase. That's the particle motion moving back and forth. Yeah. Stratified is just when we have layers. Yeah. And if it's stably stratified, then the heavy layers are below the light layers. If it's unstably stratified, then the heavy layers are above the light layers. And you're about to undergo something called mixing. Okay.
So if phase horizontal with X, the waves are propagating in the X direction, so then it just goes up.
Exactly. And this is this picture. What? What are you saying, Mateo?
So then each one of those lines is like, or each one of those waves is like represent like a different layer.
Yeah, so here we have a fully stratified atmosphere, right? It's cold where? Up in the very top, even though this looks snowy down here. It says, oh, it's so cold down here and it's hot up there. No. It's hot down, but it's hot for atmosphere. And it's cold up here. And each one of these is layers. Now, let's have a look here. We said the frequency, for example, can at most be n. How is that changing as we go up? How's the density changing?
All those stuff.
Getting smaller. So does n get bigger or smaller?
I think it's bigger.
It's bigger. Okay, and then what about this one? PDZ.
There's less pressure as you go up.
So this is the slope of the pressure,
Oh,
right? Is that changing as you go up? Not really. Right?
you said it's a constant for like this scale, what we're doing, or? Okay.
Yeah, kind of. I mean, at least in this Pascal range. Okay. Does that make sense?
So sound will travel farther with less pressure?
No.
Yeah.
No. No, that would be cool. You get into space. Hello. No. So you need density, right? So this is talking about waves that are occurring. Remember how we started this problem at all? These are not necessarily your compression waves. These are your waves moving up and down. Right. Okay. Anyone lost? It's okay if everyone's lost. We will come back to this. Okay. So I'm trying to tie these ideas together. And the place that we're going to tie these together really well is when we see them in geostrophic flows, when we see them in geodynamic flows. Okay. Because then rather than just thinking about a single layer of air, you're going to think about the whole layer of air moving together. We're going to add these two ideas. Okay. But first we have to do rotation. Okay. People trust me? Is that okay? Okay, so now turn to chapter 4. So we're gonna go way back. We're gonna talk about rotating reference frames. Okay. So Galileo was like, oh, it's easy. You're in a cart, right? Being pulled by your assistant. You see the world same way they do. So you have some reference frame. And then you have another reference frame, which is moving with a P. And let's say this is the original reference frame O. This will be O prime. This is X, Y, Z, prime, X prime, Y prime, right? And if I have a translation, it's fairly straightforward. It's just the kinematic equations. X equals x naught plus vt. Right? Z equals z. Because that's just moving to the right. Becomes a little more complicated when you have rotation. People done rotation before? Everyone's taking classical dynamics, right? Okay, so you're all masters at rotational dynamics. Obviously, otherwise you wouldn't even be taking this class. So here's the way we think about it. Here's our 1, 2, 3. That's the original reference frame. And this is another reference frame over here. Okay, this one is doing a little rotation. One for spin. Okay. And from the perspective of the viewer or the thing that we're looking at, we're going to describe the fluid in terms of a rotating reference frame. And this is going to add new terms that we have to deal with and we have to understand intuitively. Okay. So you can follow this geometry if you want, but it's not that difficult if I just write all the terms out and we think about what they mean. You're essentially going to get 4 new terms. What? Let's go back here. Okay. You're going to get 4 new terms. Do you see them? Do you see what I see? Where?
2 kappa omega.
Here. Good. So is this term,
And then the d omega dt.
d omega dt, that's another term.
The x prime minus omega. Oh, all that is in this.
Is this one or where is it? What's the term?
I thought the those are curled, right?
Yeah, these are curled, right?
Okay, I thought they were like 2 different things, so like.
So it's gotta be one term. Right? What's that? Okay, good. There's another term right here.
Mhm.
What do they mean? Let's start with the first one.
Mhm.
Let's go back to our picture. And let's imagine that in fact, we are not rotating. If omega equals 0, okay? What happens to these terms? This one's gone. This one's gone. And this one's gone. But what is this term?
The movement of the frame itself.
There we go. So that is this term here, right? That's the movement of the frame. V is du dt. Well, wait a second. Du dt would be the, not just movement, but the du dt. U is a velocity. The acceleration of the frame. These are non-inertial reference frames. Okay, this is an accelerating reference frame. So what does du dt mean? How do I experience a du dt when I get in my car? That creates it, but what do I feel?
It's like gravity.
Oh, you go the opposite direction with your vertical.
That car goes, yeah. All right, Mateo, slow down. Right? That's the du dt term. Acceleration of the frame. It creates a fictitious force. No one outside of the car thinks that you should have felt the force. Why are you crying? It's not that fast. 10 G's, relax. You pass out? Come on. Okay, that's your fictitious force. What's this one then? Let's do this one. This will be easy. There's another time derivative.
Is that how fast the rotation is actually happening?
So that's so rotation is the big omega. Let's take a reference frame and let's rotate it.
That's like rotation is changing.
That's rotation is changing.
Oh,
Okay. So for the most part, when we do geodynamic flows, what is d big omega dt? Hopefully. Right? Why hopefully?
The earth is slowing down.
Yeah, both of these are correct. One, too complicated, and two, if the Earth is slowing down and speeding up, you're in a big trouble.
Yeah.
More
You're having a bad day. Okay, it's not like the core, right? Whatever that movie is called, core spins up or something. Right away, right away. Okay, so then we just have two more terms, and these are the ones that suck, right? So you have this one and you have this one. I don't like those ones. Curls don't mean anything to me. But in fact, we will know them intuitively. But without looking at your book, I know that's impossible. What are we looking at? What do these two terms mean?
The one at the very end, the bracket.
Yeah.
Like, did you already do 2 omega across U? Are we doing that one and the last one? or-
Yeah, so these ones I like to treat sort of similarly because they have a very intuitive feeling. They don't require understanding of DDTs. So this was the linear acceleration of the frame. This was the angular acceleration of the frame. These two, they look similar, right?
Is the 2 omega across U just the fictitious force is stronger as you go outside with the axis of rotation as you get farther from it?
So what tells you that about this?
Because you would be getting larger, so the cross product won't get. Because U prime is the distance from the center of that of the.
But U is not a distance.
That's it's the vector, right?
Right, but how do you get a distance here? I'm not saying you're wrong, but this is not a distance.
No, it's the vector.
I know. But it's a velocity.
Yeah.
Right? U is a velocity, isn't it?
Yeah.
I'm not saying you're in the wrong. There's two terms here, right? One here, one here.
Wait, is X prime also a velocity or is that the distance?
Ah, good question. This is what? Remember that the primes here mean new reference frame, not derivative. We do not have primes and fluids being derivatives. We have DDTs and we have partials.
So that's just a position.
So this must be the position in the new reference frame. So this one can fit the bill that you said, right? But what did he say? What did that mean? Perfectly drawn circle, amazing. Okay, if I stand in the middle, how fast am I moving? I'm not moving. I'm just finishing. Okay. Well, I have a finite width, of course, maybe my wrong. But if I stand over here, then I get speed. Then I get speed from the fact that the reference frame. Right? That's your feeling right there. What's that called again? Nope. Right. This is your centripetal or your centrifugal forces. Right? Centripetal acceleration, centrifugal forces, fake forces that exist in a rotating reference frame that depend on your position in the frame. So if you're close to the axis of rotation, you feel less centrifugal forces. So on the Earth, people agree that we're on the Earth?
Yeah.
Okay. No, not Kobe. Everyone but Kobe. Let's say we go to the North Pole. Do you weigh more at the North Pole or the equator? And assume you don't walk it and lose a bunch of weight. What was that?
North Pole.
North Pole. You weigh more at the North Pole. That's why Santa Claus is so fat. Of course, that's a lie. I didn't mean that. So this is what it looks like. Okay. This is called an equipotential surface. We think about it in the context of rotation. Here I have a sphere. The sphere would be, say, the Earth. And as it rotates, no. Okay, as it rotates here, okay, there's a greater gravity pulling it in compared to here where it's being flung out, right? Because of the rotation. And therefore it gets wider this way, it's smaller this way. Is your question? Yep. Oh, okay. Start with sphere Earth. Okay. And then spin it. As I spin the sphere Earth, at this location, there is no additional acceleration due to the rotation. It's just living its best life. Okay. But over here, when I go to the edge, this is now moving quite quickly and it's getting flung out in the same way that we get flung out on our merry-go-round. Right, you stand near the edge, it's flying out, right? Okay, so this begins to deform and the surface of the earth moves. And earth gets fatter at its waist. And as this moves out, this moves down. Because now there's less stuff supporting it from below. And it becomes an ellipsoid. And we can measure it, yeah. Is that what? Yes. So because we are at the North Pole, let's say we're standing right here, now it's just all gravity pulling us down. Whereas here, you get a little bit of a little bonus, right? Because you're being flung off the earth, your weight is slightly off balanced. Now, effectively, you won't notice this. This is not like a weight scheme that you could possibly sell to someone. You know, I lost 14 pounds and all I did was move to Ecuador, right? Won't work. But for the purposes of geodynamic fluids, it does matter. And in particular, what we want to think about is we can kind of get over this by just realizing that G here doesn't necessarily point to the center. Okay, what does that mean? These are body forces that happen to the whole fluid. So as the fluid is rotating, we can just change the direction of that G. Instead of being at the center, we're going to make it slightly off center. Okay, taking into account both of these forces. The center, if the thing is not spinning, and slightly off center from the radius out to where you are. If, like, let's say you're up here, it's almost all down. Whereas if you're working here, it's going to be more strong, right? Towards the center. Tilted away from just the middle, be tilted just straight down. Does that kind of make sense? Okay. Good. Oh, fuck me. I never have time. Who gives these class times? Okay, last one. What's this one? It's got to be the Coriolis process of elimination. So what we'll see is we'll see this again, and you're all going to have it perfect. So we're going to take this one. Eventually, we're just going to buckle it into here. We're going to call this special G.
Okay.
Okay. And we're going to say this one sucks, and we don't want to ever see him again. But I will make you see him next week or next Wednesday. And I want you to know what this is, but we will describe it more. And then we'll talk about geostrophic flows. And we'll use that same idea of these, like, the earth is big. And all of the fluid is happening. Essentially, if you think about a basketball really quickly, place a piece of paper on the top of that basketball. That is all the air and all of the water. Now, that's probably too much space. So when you think about it, it really is like large horizontal scales, tiny vertical scales. Okay.
Wait, what's the scale comparison you use?
Basketball.
Yeah.
Piece of paper. That's the whole atmosphere. That's the entire ocean put together is that piece of paper. And the ridges on the basketball, they have to be gone. Smoother than a ping pong ball. Smoother than a billiard ball. Smoothest thing you can think of. Our little baby mountains, nothing to the earth. Okay. All right. Any questions?
Yeah, I didn't get the instructions for 8.3 of the homework.
Okay.
Am I supposed to like do the problem or am I supposed to do the other thing that?
It's an or.
Oh, or okay. got
You
it.
can either do 8.3 or you can code up the examples that we talked about with gravity waves. Yeah.
Either.